everyone, my name is Gil Hernandez, and I'm an instructor at Treehouse. At Treehouse, we offer unlimited access to hundreds of hours of courses, workshops, coding challenges, and learning tracks at our website, teamtreehouse.com. If you like this style of this course and want to learn more about programming, check out the link in the description. I'll see you there. In this course, you'll practice a way to write JavaScript called Behavior-Driven Development, or BDD. In BDD, we write special functions called tests for our application before we actually write any real code. These tests describe how our code should work. In other words, tests describe the expected behavior of our application. Having these tests written already will help us understand the code we want to write, like an outline. As we continue writing our code, our tests will let us know as soon as our programs behave the way we want them to. They'll also tell us when we've accidentally broken something along the way. We'll build up our tests to cover one small unit of our code at a time. This style of testing is called unit testing. Since unit tests focus on small, meaningful chunks of functionality, good unit tests are easy to understand. They prove that each piece of our code does what we want. In the next video, I'll cover some of the ways unit testing makes development easier. When developing, we're constantly in the process of testing things. We write code, check that it does what we want, and make sure nothing else broke in the meantime. As we're starting out, we usually just write some code and then run it to see if it breaks. For example, we might write a function that adds 3 numbers together. How do we know that we're done and that the function works? We probably load the function in our terminal or in the browser console and just see what happens. Even though this tells us whether our code works, it doesn't tell us very much about why it fails when it breaks. JavaScript programmers also often add console.log statements to track variables and functions, what the this keyword refers to, if their math is correct, and whether things are happening in the correct order. Consider this gather names of function, which expects an array of people objects with names. It should return a new array with just the names of each person. Have I written it correctly? Maybe you can already see whether it will work. In order to check, I might just try running the code here in my browser console to see what happens. Well, I see that it doesn't throw an error right away, but I still haven't proven that it works. I only know that it's valid JavaScript. Next, I might try using the function with a quick example. So in this case, I'll pass an array of people into the function. Then save the output to the names variable. Still, nothing broke, so that's a good sign. But again, I haven't actually proven that gather names of does what I want because I haven't actually seen the value of names. And if I add a console.log, you can see that names is not what I expected it to be. All their names are undefined. And now I still don't know what the problem is. Even after all this generic manual testing, I have more debugging ahead of me to fix this function. So this method of checking code is very tedious, and in the end, I'm still unsure of what went wrong or how to fix it. So a number of things makes this process very low value. First, I was only able to see one specific piece of my code. We only have one function in this case, but imagine if I had a big application spanning multiple files and interacting with one another. I would have to repeat this process across the whole stack to find a problem, taking even more of my time and energy. I also have to add a lot of code to my real application just to make the tests work. Now, I've loaded up my code here with silly variables and arrays and function calls that I don't really need. I just put them in here to see what's happening inside the program. That makes my code harder to read and changes the way my program runs. And I also have to remember to remove everything I wrote just for testing before I really publish my code anywhere. For example, var people and var names don't really do anything in my application. They're just example tests I used to figure out what's going on. And if I forget to remove any of these statements, my application might break and cause more headaches. Also, even while I'm debugging, I have to remember what all my console.log statements actually mean. Usually that means I have to spend extra time typing little notes to myself from inside every console.log. Again, we only have one here, but if I were manually testing a big application, there might be a lot of these log statements illustrating the issue. Most importantly, these are just temporary fixes, and they don't increase your ultimate confidence in your code as it continues to grow and change. So what happens if I change the way gather names of works later? I'll have to go back and add all of these statements again, and maybe have to totally rethink what I'm testing. And I won't know if my changes affected other parts of my code that depend on gather names of without testing those as well. There's a better way. We'll still always need this method of guess and check development, but we can accomplish a lot of the same things more succinctly using automated tests. In the next video, I'll show you an example of how automated testing improves our development in all these ways. In this course, we'll be using a tool called Mocha to write automated tests for individual units of code in our application. We'll build a collection of test functions called a suite. Mocha, like all testing frameworks, lets us run all of our tests whenever we want to, so we can make sure our functions run as we expect them to. This will increase our confidence that our code is working, and it will make understanding problems much easier. So let me show you how easy it can be. Developers use the term test suite in different ways sometimes. Some use it to refer to the whole collection of all our tests. Sometimes it means a particular selection of tests that are related. For example, all the tests for logging into our website might compose a test suite. Now, the team that designed Mocha uses suite to describe a specific group of related tests, so that's how I'll use it too. Just be aware that some people use it in different ways, and you might have to ask someone what exactly they mean, depending on the context. So I've already written a test suite for our tiny gather names of function we used in the previous video, and don't worry about what any of this means yet. I'll talk a lot more about how to write a test suite and what it looks like soon. For now, I just want to show you how Mocha runs tests. With Mocha already installed and my test set up, I can go over to the console and simply type Mocha followed by test. And Mocha automatically runs the tests to check that the function behaves the way we expect. So we can see here in the output that gather names of looks good in our first test. It returns an array, and the array is just as long as the array we pass in. But then it fails when we expect it to give us the name back from the object. We can see that gather names of returns undefined instead of the person's actual name. And when I'm ready to go fix this function, Mocha tells me that I can check line 23, column 25 of my utility spec.js file to start debugging. So the error Mocha is reporting is just helpful enough in this case. So it says expected undefined to equal Gunter. So that means our function is returning undefined at some point instead of Gunter. So if I go look in the gather names of function in my utilities.js file, I see one return statement for my array, but the function being used by map doesn't return anything. I'm getting undefined in my new array because gather names of checks for a name, but never returns it. So I'll fix this function by adding return before person.name. I'll save this file, and when I run the test again by typing Mocha tests, we can see that they all passed. So great, now I know that the function is working. Don't worry if this doesn't make a whole lot of sense just yet. It will all make more sense later. The main takeaway here is understanding how automated testing solves a lot of the problems with manual testing we noted in the last video. First, our test suite could cover every important function in our code, and when we run the tests, we can see all of the results nicely displayed in an informative way, so we don't have the problem of our results being too narrow. And second, the test files are completely separate from our real code, so we don't have to make any changes there or clean up our live code later. Third, the output is easy to read and understand, so it's much easier to interpret what we're seeing here than in our console.log statements. And finally, good tests guarantee that our code works the way we expect. We can run the tests over and over anytime we make a change anywhere and instantly see whether anything new has broken. We'll even see what the specific nature of the problem is. As you learned, automated tests handle a ton of the hard, tedious work we were previously doing by hand. It makes our code more reliable, it makes programming less frustrating, and the benefits scale more and more as our applications grow. The kind of automated test we'll learn to write in this course are called unit tests. Unit testing involves writing tests that confirm an individual function or piece of code works the way we want it to. We write unit tests for code that has a clear, specific purpose. For example, we'll often write unit tests for the individual functions in a program. The unit test can then call the function without needing to run our entire application to make sure we know that the function behaves as we expect. Unit tests are kind of like a basketball drill. As a basketball player, you need to master various skills like shooting, passing, running, dribbling, and so on. Basketball players run specific drills to test each of these skills outside of an actual game. A basketball player might just practice free throws for a while, and then practice dribbling at a different time, without worrying about shooting or passing or what their teammates are doing. A unit test is like one of these drills, and we can run unit tests constantly during our development process to ensure that everything is working every time we make a change. But being good at each single thing isn't enough to be a really good basketball player. They also have to be able to do them all together. In addition to practicing each individual basketball skill, players practice drills as a team. They need to make sure that they can dribble, pass, and shoot just as well when there are other people doing their part around them, and that they can do them all together in the correct sequence. In programming, this kind of testing is called integration testing. You use integration tests when you add new code to pre-existing code to make sure that not only do all of the pieces work individually as expected, but also that they run together correctly without breaking. Product managers or people who run open source projects might also run integration tests whenever others write code to contribute to their projects to make sure that the code others write doesn't break their existing project. That's useful. On a basketball team, it's not enough that your skills are up to par and that you work well together as a team. You also have to play actual games. Live games are very different, even from practice games. We play basketball on different courts, with different crowds, and against teams with different strategies. So being a good basketball team requires a lot of team experience in this context. In software, this kind of testing is called end-to-end testing. We fire up the application and run it from start to finish for all the user stories we can think of. This ensures that the program is ready to go live and that the special details of deployment don't screw up the stuff that we carefully tested on our local machines with unit tests and integration tests. We conduct end-to-end tests very occasionally, maybe only a few times during a product's lifecycle, as they're very time-consuming and expensive. You might conduct some or all of these kind of tests where you work or in your personal projects. We'll focus on unit testing in this course because that's what you'll spend most of the time writing. Unit tests actually help us write better code and grow as developers as soon as we start using them. So we're almost ready to dig into writing some unit tests. I hope you're excited as I am. Before we do, I want to talk about behavior-driven development, or BDD. BDD isn't a type of testing, like unit testing or integration testing. Instead, BDD is an approach to building software. If you've ever written an essay or a story, you probably noticed that it's really hard when you don't have a plan. You forget what you wanted to say, or you don't say quite what you mean, even if you spend a lot of time writing. So it helps to start your writing process with a brainstorm or an outline so that you can always have an idea where you're headed. Behavior-driven development is like creating a plan before you write your program. Instead of writing a bunch of code and then seeing if it works, like a lot of programmers do, with BDD you write tests first and code second. Now, this may seem counterintuitive, but BDD makes us start by describing the behavior of parts of a program. How should this function behave when something happens? What should we expect to get back from this function if we give it a number instead of a string? In other words, we start by describing how the program should work. These are our tests. And then we write code until it does work the way we expect it to. At first, our expectations will not be met because the functions we're testing don't even exist yet. So the output of these errors will be bright red, and that's okay. Then, step by step, we code our function until the tests pass. That is, until bright red errors are replaced with passing green check marks. As we fix the errors one by one, we get new errors that give us guidance in writing the next piece of our function. At first, you don't worry about the code looking good or being efficient. You just want to see the tests pass. If our tests are good, we can be confident that our functions really do what they're supposed to. At this point, we can now go back to our function and change things around to make it nicer to read or faster to run. This process of improving our code is called refactoring. Now, the great part of this process is that once we have our tests in place, we'll immediately know when a change to our code breaks our application's functionality, a red error indicating a failing test. This development cycle is called red-green refactor. First, write the tests, even though at first they'll fail. They might not even compile correctly at first if they refer to things that don't exist yet. Second, fix the function in the first way that comes to mind, just to get our tests passing. And third, go back and refactor the function for improvements, repeating the cycle until we're ready to move on. In the next video, I'll show you exactly how to do this with some clear examples. To show you how BDD and the red-green refactor cycle helps us, let's imagine we have an application pulling movie titles from different sites on the internet. Because the information comes from multiple websites, we can't be sure that the titles coming in have the style we want. We want the titles in our database to be nicely title-cased, which means that the first letter of every word is capitalized, except for certain less important words like the, and, of, and so on. I've linked to some examples of title case in the teacher's notes as well. So let's try writing a function that can handle this title casing for us using BDD principles. First, let's install a testing tool called Chai. Chai is what's called an expectation library. Chai includes special functions that throw an error when an expectation is not met. For now, we can use Chai functions to write our BDD outline for a small function. You can follow along in workspaces or in your own command line terminal on your computer. Okay, so first, we need to install Chai for our project. So in my workspace console, I'll type npm install Chai, followed by --save -dev. So I'm using the save dev flag here for my npm installation instead of just save, because Chai won't be a dependency for our working code. We don't actually need Chai or any of our testing tools in order to run our application. We just need it for our development process. Now, if you forget how to set this up, be sure to check the teacher's notes for a link to Chai's documentation and installation instructions. Next, I'll create a new JavaScript file by going over to the console and typing touch textutilities.js. I'm calling my JavaScript file textutilities.js because the title case function we're going to write is just a tool for manipulating text. Once again, you can refresh your sidebar to see the new textutilities.js file. So when I open our textutilities file, the first thing I'm going to do is import the stuff we want from the Chai library. We specifically want to use the expect method. Check the teacher's notes to read about other methods you might prefer, but I'm just going to use expect for the rest of this course. So to import expect from the Chai library, I'll type var expect equals .expect. Remember, to import stuff, we write require followed by the name of our library as a string. So inside the quotes, I'll type Chai. And now Node will know to go look for a package with that name in our Node modules directory. Now, you might not have seen this style of require statement before, but don't worry, since I don't want to use everything in Chai, I'm just saving the expect method to a variable and throwing the rest away. So writing it this way is a more efficient way of writing it like this. So var chai equals require chai, followed by var expect equals chai.expect. Now that we have the expect function in our file, we can use it to write some expectations as our outline. To use it, we write expect and pass in a value we want to use for comparison. Then we chain some special chai methods to tell chai what we expect that value to be. So for example, we can say expect true dot to dot be dot false. So expect true to be false. Now, this is obviously going to fail because true does not equal false. So if I save this and run our test file in the console using node followed by the name of our file, which is textutilities.js. Once I hit enter, we see that I get an error. It says assertion error, expected true to be false. Cool. So now I can go back to our code and fix this example so that it's passing by switching false with true. And now if I run node textutilities.js again, we don't see any output at all. So there were no errors. We're going to see a lot more useful output when we combine chai with our unit testing framework Mocha in the next stage. But for now, this will be our green. All right, so now let's write our first expectation for the title case function. So I'll start by writing expect title case, and then pass in an example of a movie title our application might be sent from the internet. So I'm going to type The Great Mouse Detective. Notice the title has no capital letters. I'm just making this up as an example for me to test against. I could put anything I want to in here. This is just acting as a guide for me as I write this function. So what do I expect the output of our title case function with the Great Mouse Detective to be? Well, I definitely know that I should get a string back, right? A string goes in and a string comes out. So let's start with that. So I'll say dot to dot b dot a string. So expect title case, the Great Mouse Detective, to be a string. With my first expectation written, I could go run our file again in the console with the command node textutilities.js. And this gives me an error now. It says reference error, title case is not defined. And that's right, because I haven't written the title case function yet. Now, we should fix just one error at a time. So let's make this go away. Back in my textutilities.js file, right above the test we just wrote, I'll write a new function named title case. So I'll say function title case. So now when I save the file and run the file again in the console, I see that I stopped getting a reference error. Instead, I get an error that says assertion error, expected undefined to be a string. Perfect. It looks like we're making progress. Now, at this point, I know that title case is going to accept a string as an argument, and it's going to do some stuff to it and give me back a new string. So I can get our current test to pass by doing just that much. So if I let the title case function accept a title and then spit it back out by typing return title, once I save my JavaScript file and run the test again in the console, great, we can see that it meets our expectations. But our expectations aren't really accurate yet, right? And this is an important lesson about testing. We can pass all our tests even if nothing works correctly, if our test code doesn't really test what we want it to. So in the next video, let's add some more expectations to flesh out our outline. We'll be talking a lot about how to do this during the course. For now, I've linked to an article in the teacher's notes about ways we can make our expectations really informative. Okay, so let's start on a new line and still keep our first expectation so that if anything breaks along the way, we'll know why. And you can also go ahead and remove the simple test expectation we wrote in the previous video. I'll also go ahead and get rid of the comments. So now I'll write a new expectation by typing expect title case, the Great Mouse Detective. Now, we don't just want the same string back, right? We want the function to give us a different string. So in our example, the return string should be the great mouse detective with correct capitalization. So let's start there. This time I'll write .to equal the great mouse detective. Notice how each word begins with a capital letter. Now, if we save our file and run this in the console by typing node textutilities.js, we see that we get an assertion error. It says, expected the great mouse detective to equal the great mouse detective, capitalized. Of course, because right now, our title case function just returns the same string we put in. So to make this test pass, we basically need to make our whole function work. Now, that's a little bit too big, and it's not very helpful for this test to just tell us, make it work, like it's doing now. So we should break this up into smaller expectations that we know how to tackle. Usually, when writing tests, the most comprehensive expectation should be written last. That way, the function passes all the simpler tests first. So we'll keep this to equal expectation at the bottom of all tests so that we know when we've finished. Then right above it, we'll write a new test. So now we should think about the smallest piece of the problem we know how to solve. So what if we passed in just one letter? That shouldn't be hard, right? The function would just return the same letter capitalized. So our expectation should be something that captures that. So we'll say expect lowercase a to equal capital A. So now when we save the file, go over to the console and run our test again, we can see that it doesn't work yet. We get the assertion error expected lowercase a to equal capital A. Okay, we can definitely do this because it's built into JavaScript. So back in the text utilities file, I can call the to uppercase method on our title. So now if I save and run the test again, we see that we passed our new smaller test and we still failed the final test, but for a different reason. So now we're seeing the assertion error expected the great mouse detective to equal the great mouse detective. So all caps versus the correct capitalization. Well, this is good progress, but now we're capitalizing too much instead of not enough. So now let's add another expectation with a bit more complexity. So right below the expectation with just stroke, say expect title case to equal. And this time, let's use a single word title, but more than one letter. So first, I'll type the title vertical and all lowercase letter. Then I'll type vertigo with a capital V. Running the tests gives us the same problem as before, but it helps to keep the problem small and comprehensible by confining our expectation to only one word. So instead of uppercasing the entire title, let's target just the first character in the title. This time, when we run the tests, we get expected capital V to equal vertigo. Right, because we're only returning the first letter. So back in our function, let's add the rest of the title in, skipping over the first letter. So right after to uppercase, we'll say plus title.substring, and we'll pass 1. So I'll run the test again in the console, and great, it looks like we passed our vertigo test. So now our final test says, assertion error, expected the great mouse detective to equal the great mouse detective. So the first letter capitalized versus the correct title casing. So we're getting closer. We know how to capitalize the first letter of a string, We know how to add strings together. We just need to do this for each word in the title. I think we're ready to try making it work. We have a pretty thorough understanding of the problem at this point, and several tests to keep us on track if we misstep. Okay, so we know what to do with one word. If we keep our final test case in mind, we know we need to break the string apart into several pieces so that we can do our one word part on each word in the title. In the title case function, we can start by splitting the title up at the spaces. I'll type var words equals title.split. And I'll leave a space inside the quotes. So now we have an array of individual words from our title. Now, before we even get stuck figuring out the middle, I like to write the return statement because I already pretty much know what it will look like. We know we have to give back a string that's been title cased. We know that somewhere in this function, we have to put all the words we just separated back together. So we may as well do that in the return statement. So I'll write return title cased words dot join. I know I have to join them back together with a space because that's how I took them apart. So right now, I'm going to just guess that I'll make an array called title cased words because I know I have to transform all the individual words from my words array somehow. All right, so now that I have the start and end of my function, a lot is already done for me. I know I need to make this array title cased words, and its value will be derived from the words array. So I can at least type var title cased words equals words. Now, here's the logic part. I need to loop through all the words, do my title case logic on them, and then store them in title cased words. So let's see. Do you already know a function that will do something to each member of an array and give me back an array of the same length? Yep, that's right. The map function can do that for us. In fact, we used this for the gather names of function in the first video. So back in my title cased words variable, I'll add the map function right after words. Next, I'll move all my title case logic for one word into the map callback. And now I'll get every word title cased in my title. So in the map callback, I'll pass word. Then in the return statement, I'll change title to word. So now when I save my JavaScript file and run the test again in the console, great, it looks like everything passes. This function isn't quite finished. I'll talk more about covering edge cases in the next stage. So far, we've made a lot of assumptions about the input for this function. For example, we've always started with a completely lowercase string with no punctuation or weird characters. But what happens if we get a title that isn't nicely formatted already, like this title? We might need to expand our function to account for these things. For now, try and imagine a simple expectation for the title case function that would fail. Remember, titles don't really capitalize the first letter of every word. They skip less important words. So you can try fixing the title case function to practice your BDD strategy and get more comfortable writing expectations with Chai. Even if we had been overwhelmed or confused about where to start with our title case function, BDD helped us break the problem down into smaller and easier pieces. As we worked towards passing tests, we got a better and better function. Not only did red-green refactor help us write our code, but now we actually have some simple tests for our function too. It might seem strange at first to just think about these tiny examples and expectations, but the secret is that this is one of the easiest ways to program. Once you get used to writing unit tests, your code will also be better because you'll have thought about it much more carefully. You'll even have tests for your functions that you can show other people to explain what your code does or get extra help. That's pretty cool. In the last stage, we talked about a style of development called behavior-driven development, or BDD. It means we write unit tests as a guide or outline before we start writing our application code. We practice this strategy using an expectation library called Chai. In the example code we wrote, our expectation functions were included directly in our running code, and they didn't have significantly better output than console.log statements. As you'll learn in this section of the course, the professional approach to writing unit tests is to put your test code in a file that's separate from your application's code. I'll show you how to do that. The important thing to keep in mind, and what separates unit testing from logging to the console, is that tests describe expected behaviors. Unit tests focus on the concrete output of functions without worrying about how the function does it. Now, we could have written our title case function in any way that made sense to us, as long as it ultimately produced the end result or behavior we expected. In this stage, we'll use BDD to build a game engine for a digital version of Battleship. We'll use a testing framework called Mocha to make our BDD approach even better. We can keep all of our test functions in a separate file and even set them up to run automatically anytime we make a change, so that we'll know right away whether we're improving. To get started, we need to install Mocha. Go ahead and follow along in Workspaces or in your own terminal. Since we're starting a completely new project, I'm going to start in a new workspace. Now, I named this workspace JavaScript Unit Testing Basics, but if you're following along outside of Workspaces, you can name the project directory on your computer Battleship Engine or something more meaningful. So in order to have Mocha and Chai in my project, I can type npm install, followed by the save dev flag, then Mocha Chai. I use the save dev flag here because these tools are just for development. And once they're installed, you can see the new node modules directory that includes the new libraries by simply refreshing the workspace sidebar. With Mocha now installed, we can call Mocha, followed by the name of a JavaScript file containing our tests from the console, and we'll see the test results output there. So for example, if I create a new file called main_test.js, then in the console, run mocha main_test.js. Mocha prints 0 passing in green to my console because there are no tests in main_test.js to pass or fail. But we don't always want to run Mocha specifically for each test file we might have. A large project might have many test files all around, and it would be annoying to run each one individually. So in the next video, I'll show you how to set up our test files to make this really easy. Different frameworks require us to set up our file structure differently. They want us to name our test files differently or put them in different places. The main issue is that we don't want to track down our test files manually every time we run them. The whole point of automated testing is that our tests are easier and better to use than our old manual testing style. If our tests are annoying to use, then we might go through all the trouble of writing them only to never actually run them while we're developing. That would be a huge waste. So we want our tests to be easy to run and write. That way, we're more likely to actually test our code. Mocha has a really convenient feature. Since we've already installed Mocha as a dependency for our project, we can have npm use it to run all of our tests automatically. So first, in the console, we'll run npm init. This sets up our project to be portable, and it takes advantage of some convenient npm features. Now, in the console, npm asks us a bunch of questions about our project setup. But for now, I'm just going to press enter for all of these and accept the defaults, since I don't plan to publish this project anywhere. The result is that we have a package.json file for our project. Now, it doesn't have much in it right now, but notice that the scripts field has a test method already. By default, the test method will normally just give us a warning in our terminal or console that says error, no test specified. But in our package.json file, npm has already set the test command to use Mocha. And although we've been explicitly telling Mocha which files to run, we can actually save even more time by keeping all of our test files in a directory called test. It's important that the directory is specifically named test, not tests or test with a capital T, and it has to be located at the same level of our project structure as the package.json file. It makes sense to have all our tests in one directory at the top of our project. It makes it easy to pull in code from other files in our project because the file path will always be from the same directory. It also makes it easy to organize our tests and for ourselves to find the right test file after we see its output in our console. Now, if we forget to install Mocha before running npm init, we can always just go change this part of our package.json file by hand. And you can check the teacher's notes to learn more about customizing your package.json file to run tasks for us, like starting our automated test script. So if we follow these guidelines, then we just get to run npm test, and Mocha will automatically run every single test in the test directory for us. So let's create a new directory called test here at the root of our project. And I'll move the main test.js file inside the new test folder. So now when I run npm test in the console, I get the same output as running Mocha. Great. Earlier, I mentioned that it's important that the directory is specifically named test in all lowercase letters. Naming the test directory badly is a common mistake developers make when setting up suites. So let's see what Mocha's output is when we use a directory name other than test. For instance, let's change the name to tests, then run npm test in the console. So now Mocha can't find what it's looking for. So we get this test failed error in the console output. And the same would happen if the name is test with a capital T. So I'll change the name back to test, then run npm test in the console. And now Mocha, once again, automatically runs every single test in the test directory. Okay, so in the next video, we'll really start building our first test suite. Let's open up our main test.js file and start really using Mocha. The first thing to do is set up a test suite. Remember, a test suite is a block of unit tests that are all closely related because they test the same function or they test similar parts of our code base. We introduce a test suite in Mocha using describe. Describe is a function that takes two arguments, a string and another function. We use the string to describe what the suite will cover. So for example, let's write a test for ourselves to prove that Mocha is working properly. This kind of trivial check is called a sanity check because it's easy to write and it verifies that all our code structure is in proper order before we get started. Doing this now will help us confirm that things at least worked at some point, even if we experience bugs later down the road. Since we're testing our Mocha framework, I'll just write Mocha as the first argument. Mocha is the thing we're testing, so that's a good title for this suite. Now, the second argument is an anonymous function. It doesn't require any arguments. It's just a wrapper for all of the individual unit tests that we're going to include within this suite. So now with our suite in place, we can start adding some simple unit tests. Each individual unit test is sometimes called a spec. And just like our suites, Mocha makes it natural to write our spec by containing them in a function called it. It is similar to describe. The first argument is a string that describes the particular behavior this unit test is responsible for. And again, just as a sanity check for myself, I'll say should run our tests using npm. The second argument is a function. This time, the function should contain all of our expectations for this unit. Remember, an expectation gives a specific state condition for a test to count as passing. Otherwise, it throws an error. So let's import chai at the top of our file so that we can use it as an expectation here. So once we have the expect method, we can write an expectation inside of our lonely unit tests. So I'll start by writing something I know will pass, just to prove that Mocha has access to this file here. I'll say expect true.to.b.get OK. So expect true to be OK. Now, OK is an assertion method for chai. It tests whether some value is truthy. That means any value besides undefined, not a number, false, an empty string, or 0. So any value that would satisfy an if condition. Okay, so now if we run npm test in our console, we see some really nice output. It says, should run our tests using npm. Well, that's easy to read and informative, so it looks like everything is ready to go. In the next video, we'll start writing our BDD outline for Battleship. Let's start building our Battleship game engine. In Battleship, there are 2 grids, one for each player. Each player secretly places their set of 5 ships on the grid, and then players take turns guessing where the ships are located. If you correctly guess that a ship is located at a position on your opponent's grid, your opponent marks that spot as a hit. If a ship has been hit at every unit of its length, the ship is sunk. The first player to successfully sink all of their opponent's ships is the winner. So we'll need to write code that handles the current player and winner, the number of ships, their position, and their status as active or sunk. I know that sounds like a lot, but just like our title case function from the end of the previous stage, we'll use BDD to break all of this down into small chunks by writing unit tests. So let's start with the smallest part of the game, the ships. Inside the test directory, I'll create a new test file to contain all of the tests about ship features. I'll call the file ship_test.js. I like adding the underscore test into my test file names so that I can find them more easily later, and it's a bit more obvious what my error reports are trying to tell me in the test output. Okay, so let's import expect from chai first. So at this point, I can already guess at a few functions we might need. We'll probably need some kind of function to tell us whether a ship is located at certain coordinates. So for example, when a player puts a ship on the board, or when a player tries to attack, we need to check whether a ship is positioned at the location they're naming. So let's set up a new suite for this function using describe. And since the function is just going to check for a ship, I'll name it check for ship. Remember, Mocha's representation of a test suite, the describe function, takes 2 arguments, a string describing all the tests inside, and a function to wrap them all together. So now let's import the check for ship function here at the top of our describe function, because all the tests in this suite will need access to it. Remember, this suite will just break at first because the function we're referring to here doesn't exist at all. This is just an outline for now. So I'm making an educated guess that we'll want a special directory named GameLogic to contain all of our GameLogic functions, and that will keep all the ship-centered functions in a file of their own. So what should check for ship actually do? Well, we'll probably give it a coordinate. If there's no ship there, I think it should probably just return false. We might change that later if our functions work differently than we expect. Maybe in the end, we need it to return more information than just false. But for now, that makes sense, so we'll start there. In Mocha, a spec looks very similar to a suite. It takes 2 arguments, a string describing our desired behavior, and a function that wraps all of the specs, expectations, and logic up together. Each spec should be responsible for just one aspect of the function's behavior. So in order to describe that particular behavior of check for ship, I'll name this test spec should correctly report no ship at a given coordinate. That's really informative. It communicates what the spec is designed to prove and also some useful information about the nature of the function. The function takes a coordinate of some kind. But I just realized that this isn't enough information because there are two boards in Battleship, yours and your opponent's. So check for ship will also need to accept a player so that it knows which board it's checking for the given coordinates. So I'll change this to should correctly report no ship at a given player's coordinate. It's best to keep a tight feedback loop in BDD. Since I've written a lot of test code already, let's run our test and see what happens. So in the console, I'll run npm test. And I see that I get an error. It says error, cannot find module, game logic, ship methods. Well, remember, the ship methods file isn't even real yet. So let's go fix that. So I'll create a new folder named game_logic. Then inside this new folder, I'll create the ship_methods.js file. I'll go ahead and keep my ship test file open to compare against and just copy over any code I'll need later. So I'll start by simply defining the check for ship function inside the ship_methods.js file. Then I'll export it by typing module.exports.check_for_ship equals check for ship. All right, so that should be enough to get over the import error. So now if I go over to the console and run npm test, cool, it shows that we're passing our new tests. But we know that's a trick because that test doesn't actually contain any expectations yet. But at least we know our files are connected properly and that we set up our suite and spec correctly. Those sanity checks are helpful. So let's write an expectation for this spec now in the ship test.js file. For this spec to be meaningful, it has to call the function we're testing. So it's time to make some guesses about how this function actually works. We need to guess what kind of parameters check for ship will accept in order to use it in our spec. Now, we could represent our coordinates in lots of ways: a string of two numbers, an array, an object, and so on. So I like the idea of arrays, since they come with lots of useful methods built in that we may want to use. Again, I'm just making educated guesses right now. When I start writing the game, the implementation details might challenge our starting assumptions. So it might be easier to come back and adapt our tests than it would be to make our functions match our expectations. So the unit test we're writing just gives me a starting point that makes sense to me. Inside the spec, I'll write our expectation to call check for ship with a player and an arbitrary location where none of that player ships are located. So let's say 9, 9. And since there are no ships there, check for ship should return false. So let's add to be false. Okay, so now if we run npm test in the console, our test shows that our spec isn't quite ready. We're trying to pass check for ship arguments that we haven't defined yet. The hardest part about BDD is deciding how the function we haven't written yet might actually work. We have to make an example of the kind of argument our function might expect so that we can use it in our spec correctly. This is a lot like how we made up an imaginary array of people objects to test our gather names of function back in stage 1. The difference is that we don't have the real function in hand yet, and we're not adding that cruft to our real code files. These guesswork function calls and data structures are just going to live here in our test spec, isolated from all of our production code. The important thing is to focus on the general behavior of the function we're testing and not get bogged down in the implementation details yet. For now, I'll just invent something that will get the test up and running and kind of make sense. And if I need to revise it later, then that's okay. At this point, I'm guessing it makes sense for players to be represented as objects, since they keep track of different kinds of information. So, right above our expectation, I'll create a player object. Each player will have a set of ships. So, I'll set an array of ships as a property on the object. Again, there are lots of ways to represent sets, but I'll start with an array for convenience. Since this test only needs us to check one ship, that's all I'll add. We'll store each ship's location as a property. So I'll add a locations array to the ship and set it up with just one coordinate. Let's say 0, 0. At this point, we're assuming a lot about the structure of players, ships, and how we keep track of their location. It's a lot of guesswork up front. But even without writing tests, programmers still do a lot of guesswork as they program. It's rare that you know exactly how every part of a program works when you first sit down at your computer. So it might feel a little strange to write all of these tests before you start writing your program. Just keep in mind that most people also feel awkward when they first start using outlines for their essays and blog posts. If you feel overwhelmed by this setup, just remember that you can always work in a tighter feedback loop. For example, you could have started this setup work by only writing an object named player to make that reference error go away in our test output. Then you would start with another small step and another until you had something that looked similar to this. Okay, so now I have a player and it has one ship with one location. And if I check for a ship at 9, 9, check for ship would return false because the ship that player has is located at 0, 0. They don't have any ships yet located at 9, 9. Running the test in the console gives us a new assertion error. It says expected undefined to be false. Great, we get undefined because our real check for ship function doesn't return anything yet. So it's time to start writing our function. So back inside shipmethods.js, the check for ship function will accept the parameters player and coordinates. First, I'll declare two variables inside the function: ship present and ship. Now, I know I'm going to have some kind of conditional block because I only want to return false if the player has no ships at the given coordinates. I know I'll need to loop through all the ships in the ships array and check each of their coordinates against the one we're giving the function. So I'll just put this condition inside a loop over all the player ships. Next, I'll save the current ship within the loop to make things easier to read. Finally, I'll filter the current ship's location array down by comparing each value to the given coordinates. So again, this will filter the current ship's location array for matches against the given coordinate. Both the x and y numbers should match, so this is going to return an array containing only the coordinates that are a match. And if nothing is a match, the array will be empty. So it will be a coordinate only if there was a match. The first member of an empty array is undefined, which will fail conditional, and that's perfect. It means we only need to save the first element of the filtered array and use that as our conditional check. So if the array is empty, that means there weren't any matches to our given coordinates, and no ship is present. Right below, we'll check whether a ship is present at a given coordinate by saying, if no ship is present, return false. All right, so now I'll go over to the console and run npm test to see if it works. Great, we get all green checks for tests. Our check for ship function is looking good, but we've only proven that it will report a miss. It tells us when no ship is located at our given coordinates. But does it also correctly tell us when a ship is located at our given coordinates? Let's write a new spec that would prove it. Okay, so back inside shiptest.js, I'll just copy my current spec for no ship present and paste a new spec right below it. Then I'll adjust the description and expectation. So this description will say should correctly report a ship located at the given coordinates. This spec tests whether the function correctly finds a ship that is located at the given location. So we should change the argument we pass check for ship to match the player's one ship location. So I'll change this to 0, 0. Then I'll adjust the expected result to be true. So now when I run npm test in the console, the tests report assertion error, expected undefined to be true. Well, currently, the only time our function returns something is when no ship is found. So maybe we should add a matching conditional to return true when something is found. So in our check for ship function inside shipmethods.js, we'll say if no ship is present, return false. Then we'll say else, return true. All right, so let's run the test again. And cool, now it works. But so far, we've only tested check for ship using a single ship with a single location. So we should expand our test to be sure it still works when a player has more than one ship and when a ship is located at more than one coordinate. So again, back inside shiptest.js, I'll copy the spec at the very top and paste a new one at the bottom. Then revise my description and expectations. So I'll change this description to say should handle ships located at more than one coordinate. This spec will test the same behaviors we've already tested, but with a ship having multiple locations. So inside locations, I'll add a new coordinate of 0, 1. Then I'll create new expectations for this location and adjust the expected result to be true. So I'll simply copy this expectation and paste a new one right above it. And this will say expect check for ship player at 0, 1 to be true. Now, you normally don't want your unit test to have more than one expectation because it might be unclear to someone reading it what the test is supposed to prove. Now, in this case, since we have individual unit tests for positive and negative checks, I'm comfortable using both expectations in this unit test for brevity. In fact, I'll also add an expectation for the 0, 0 location just to make sure we can find both. And I'll set the expected result to be true. All right, so let's save our file and run npm test in the console. And great, it seems good so far. So it looks like check for ships doesn't break when we give it a bigger ship. So let's try more than one ship. So I'll copy the bottom spec inside ship test, then paste a new spec right below it. And I'll change this spec's description to should handle checking multiple ships. Then I'll change the expectations. But first, I'll just add one ship to the ships array with new coordinates. So I'll copy the first location and paste the new one right below that, and change the coordinates to 1, 0, and 1, 1. Then right above the last expectation, I'll add two new expectations for this new location. So I'll copy one of these and paste it below. And for this, I'll say expect check for ship player at 1, 0 to be true. Then we'll add another one that says expect check for ship player at 1, 1 to be true. All right, so let's save this, go over to the console, and run npm tests. So now our tests finally catch a bug. It looks like multiple ships don't work correctly. So the test passes the first expectations, which look at the first ship in the array, but the expectations aimed at the second ship fail. It says, assertion error, expected false to be true. Well, we must have made a mistake with our loop logic. Why else would everything work for the first ship, that first loop, and then break during the second? So let's take another look at our check for ship function. And sure enough, I buried one of the return statements too deep. The loop will currently check for no matches after every ship. So that means that if the first ship isn't a match for the given location, then the function returns false right away before getting to loop again to the next ship. So it looks like we need to reverse this logic a bit. We want the function to return false for no matches only after it has checked every single ship. So that means it should return false only after the loop has finished. But it should return true immediately when it finds a match. So we can just switch things around to capture this idea better. So we'll say if ship present return true, then I'll delete this else condition. Then right before the closing bracket, we'll say return false. All right, so let's save this and go over to the console and run npm test. And great, it looks like the tests all passed now. And to be double sure, we can expand the test suite a bit as a proof of concept. So let's add one more ship to the ships array with new coordinates. So I'll copy one of the locations and paste the new one at the bottom. Then I'll change the coordinates to 2, 0, 2, 1, and I'll add two new coordinates. So this one will be 2, 2, and the next will be 2, 3. And then I'll go ahead and add a new expectation that says expect check for ship player at 2, 3 to be true. So now if I go over to the console and run npm test, it works great. That was a lot of work, so pat yourself on the back for doing a great job. In the next video, we'll keep adding specs to this test suite and expand our game of Battleship. We're starting to get the hang of Mocha and BDD, and we're using it to write more interesting functions. So let's expand our test suite and see some other things Chai and Mocha can do. Now that we can check for a ship, we also need to register damage on a ship. Currently, check for ship only reports true or false depending where ships are located, but we need to actually keep track of the damage each ship has sustained too. So let's start a new test suite to describe the damage ship function. We introduce a test suite in Mocha using describe. So right below the check for ship suite, we'll add describe. Then we'll pass two arguments, the string damage ship and a function. Then we'll import the damage ship function from the shipmethods.js file at the top of our suite. So what do we definitely know about the way damage ship should work? Well, it should probably take a ship and a given coordinate of the ship as arguments. And we need to know which ship to damage and which spot to register damage on. So that sounds like a good expectation of damage ship. So we'll create a test spec that says it should register damage on a given ship at a given location. So now that we're dealing with a given ship, this function doesn't need any information about the player object. So I'll set up the simplest ship I need to conduct the test. I'll add one ship, one location, then I'll add a damage array to keep track of the damage it's taken. So now I'm going to write the minimum function I need to get the test to run correctly. So damage ship is different than check for ship in that it doesn't return anything. So we can't just plug it into our expect method. Instead, we have to test the side effects of damage ship after we call it. So inside our spec, if we call damage ship, then pass ship and the coordinate 0, 0, what should we expect to be different? Well, we should expect the ship's damage array to be different. It should not be empty. Remember earlier when we wrote our title case function, I mentioned that Chai has a lot of assertion methods for making our tests easy to write. So let's go to the documentation and see what's available for us to use. I've linked to the BDD API docs in the teacher's notes of this video. So looking through the available methods, the very first one I see is not. And the docs even give me an example. So here it says expect foo to not equal bar. Well, that seems useful. I've already described my expectation to myself, so the damage array should not be empty. So I'll just search the page for empty and see what I get. Great, it looks like Chai has a built-in method that checks for empty objects, arrays, or strings. Cool. So this will make it really easy to write our expectation without worrying about how the real code will work. So back inside our spec, right after damage ship, I'll add expect ship.damage to not be empty. All right, so now if we save our file and run npm test in the console, we get a type error. It says damage ship is not a function. Well, of course, because the damage ship function is missing. So let's create it. So back inside shipmethods.js, I'll define the damage ship function. And the function will accept the parameters ship and coordinates. And we'll need to export the function at the bottom of our file by typing module.exports.damage_ship equals damage ship. Remember, without these module.export statements, the test files won't have access to the functions we wrote, and they'll fail when we run the tests. All right, so now let's go over to the console and run npm test. So now the test reports a new error. It says assertion error, expected brackets not to be empty. So inside the damage ship function, we'll say ship.damage.push. Then we'll pass coordinates. So let's go to the console and run the test again. And great, now the test passes, proving that damage ship can change the given ship's damage array. So now we should add an expectation that proves we actually added the right thing to the array. So let's see if Chai can help us out with this too. So once again, I'll search the docs. Now, I'm not exactly sure what to call the method I'm looking for here, but I do know that I want to check whether an array has specific members. Unfortunately, I can't just expect the first member to equal 0, 0 because two unique arrays are never truly equal in JavaScript, even when they store the same values. Every array is a distinct object, but JavaScript uses strict identity for equals. So two arrays could only be equal if they were really the very same object, not just two objects with all the same property values. We call arrays that look the same deeply equal because their deep interval values are equal, even though the arrays themselves are different objects. So I'll try searching the page for array and see what turns up. All right, so the first thing I see is a method called include, which looks like it checks for an array for a given value. This is perfect. All right, so back inside ship_test.js, I'll add a new expectation to my spec by simply copying this one and pasting a new one below. And this one will say expect ship.damage to include 0, 0. So now when I go over to the console and run the test again, I see that the test doesn't pass. It says expected 0, 0 to include 0, 0. So I can see that the ships.damage array includes the array I want, but Chai doesn't seem to believe it. It must be that include doesn't really solve our deep equality problem from before. So let's check the docs again. Now, the problem seems to be deep equality, so I'll try searching the page for deep and see what comes up. Great, so this method here looks good because it allows us to make deep equality comparisons, which is exactly what we need. So now I can write an expectation about the first member of the damage array by changing this expectation here at the bottom to expect ship.damage 0 to deep equal 0, 0. So I'll say 2.deep.equal. So basically, just check that the first element of the damage array looks like this. All right, so now if we save this file and run npm test in the console, great, it looks like everything is passing. Now, we could complicate the damage ship function by first making sure that the ship hasn't already taken damage at the given location, by making sure the location is valid, and so on. But this will do for now. Now we need a method that players can call during the game in order to fire on their opponent. It should use check for ship to confirm the attacking player's guess, and it should use damage ship to register damage on their opponent. Try and write a test suite for this fire function using some of the assertion methods you learned, like equal, not.equal, deep.equal, includes, and so on. You might even check the documentation to find something more useful for your test spec idea. The link to that documentation is in the teacher's notes of this video. And if you're feeling confident, you can even try implementing the function based on your test suite. We've already been using BDD this whole time. I think you can do it, and when you're done, I'll show you my approach in the next video. The fire function is one of the last things the game engine actually needs. Isn't it amazing how fast we can build stuff that sounded hard before we started? So here's how I wrote my test suite for the fire function. All right, so first I'll set up my test suite at the bottom of the ship_test.js file. The test suite is named fire, so I'll pass fire as the string, followed by a function. Then I'll import the fire function at the top, so it's available to all my specs. I'll skip running the initial test in this case because I know it's just going to break at first, but it's a good habit for you to keep. All right, so now I need a spec to test fire's behavior. The first thing that comes to mind for this function is that it should record damage on the correct ship if there's a hit. So I'll create a new spec that says it should record damage on the given player's ship at a given coordinate. So now I need to tell Fire which player I'm targeting and which location I'm guessing. So it should accept a player parameter and a coordinate parameter. That means I need a player object for this test. So I'll say var player. And the player will need at least one ship at one location. So I'll say locations 0, 0. And after the location, I'll add a damage array. So if I set up a simple player object and call Fire at a location I know is occupied, so let's say Fire player at 0, 0, the player's only ship should have a matching coordinate in its damage record. Basically, the ship should take damage at the given location. So let's write an expectation for that. So right below, we'll say expect player.ships 0 dot damage 0 to deep equal, and then we'll add 0, 0. So if we run the test now in the console, we can see that the test breaks at first. So now let's go ahead and set up the Fire function in shipmethods.js. So right below the damage ship function, I'll create a new function called Fire. And we'll pass the Fire function two parameters, player and coordinates. Then I'll go ahead and export the Fire function at the bottom of our file by saying module exports.fire equals fire. So now if I go over to the console and run npm test, we can see that the test gives me an assertion error. It says expected undefined to deeply equal 0, 0. Now, the Fire function doesn't yet do anything to the target ship. But I know that in the end, if a ship exists on my opponent's board at the location I guessed, I want to run damage ship on that particular ship using the location I guessed when calling Fire. So I'll start with check for ship using my guess and the given player, since this returns a true or false value. So inside my function, I'll save it to a variable named ship to use it internally. Then I'll pass player and coordinates as the arguments. So I don't need to worry at all whether check for ship will work here because my test suite has already proven that it does exactly what I expect. And that's super awesome. It takes a huge load off my brain. It's kind of like knowing that a jQuery function will just work and you don't need to second guess it. So here I'm calling the variable ship because that's what it represents. Okay, so if my opponent has a ship where I guessed, then I want it to take damage. So I know which coordinates to pass in, but how do I know which ship to pass? Now, I could run through all my opponent's ships and look for the one I want, but that's already what check for ship does. And I don't want to repeat all that logic here. So instead, let's just go refactor the check for ship method. Remember when I warned you that we might have to adjust our functions as we go? So it's okay to throw away code that was working even if we spend time writing tests for it already. In fact, this is one of the biggest benefits of having unit tests, red, green, refactor. Even though our tests for check for ship are passing, it turns out we need check for ship to work slightly different now. So our unit test will tell us exactly what breaks and how as we rebuild things. So this is an easy fix. I'll just have the check for ship function return the actual ship instead of simply returning true when finding a ship. So I'll replace true with ship. And if check for ship finds something, then I want to call damage ship on that ship at my guest location. So in my fire function, I'll say if ship then damage ship and pass the ship and the coordinates. All right, so let's see what the test reports. In my console, I'll run npm test. Well, this is interesting. It looks like all my check for ship tests are now failing because I've dramatically changed the way check for ship works. But it looks like my fire test passes, so that's good. So back inside shiptest.js, scrolling all the way up to my check for ship suite, I can quickly fix my test up. Now, my first test is fine because it still returns false when it's finding nothing. But I'll change my next spec's expectation to deep.equal. Then I'll pass player.ships 0. All right, let's go over to the console and run the test again. And I see that my test is green now for that particular spec. So great, now I know this strategy works. Now, moving forward, for all tests to pass, we'll need to make similar deep equality comparisons in the check for ship suite. So we'll edit some of our other expectations to expect an array instead of true. Now, we can simply copy and paste this deep.equal expectation across the rest of the check for ship suite, change some of the values to match the first member of an array, and everything should work great. All right, so I'll copy this deep.equal method from this expectation, then scroll down to the next spec, then replace the first and second expectation. We'll leave the values at 0, then scroll down to the next spec and replace all of these as well. So we'll change the first one from to be true to deep.equal player ships as 0. We'll do the same for the next one. And this one will change the value to 1. And we'll do the same for the next one. Change that to 1. And finally, we'll replace the fifth one and change this value to 2. Finally, I'll scroll down to my Fire suite. Then I'll create one more spec here inside the Fire suite by copying the first spec and pasting a new spec right below. I'll change this new spec's description to should not record damage if there is no ship at my coordinates. So when I change the target here to 9, 9, I would expect the damage array to be empty. So let's change the expectation to say to be empty, then remove the second 0 value here after damage. So let's see, does fire now correctly leave the ship undamaged if we guess wrong? Well, let's see. I'll go over to the console and run npm test. And yep, the test already passed. Now, I might also want to add some reporting to the fire function so that players know whether they hit or not. Since this is just a game engine, we'd probably have a separate reporting function that did fancy stuff with a DOM or printed a useful message in the console. For now, this looks really good. We have almost all the major logic for the game in place. Did you use other assertions in your test? Did you build your fire function differently? Share your solutions in the community and compare them to what you see here. In this stage, we've learned how to set up our files for Mocha, the main file structure of a test suite in Mocha, and a lot of useful chai assertions to make writing tests easy. We also did a lot of BDD to outline the basic logic of a battleship game engine. It can feel strange, but with practice, you'll find that it really is super helpful to outline your ideas first. We were able to refactor things easily and know exactly what changed in our code base. Manual testing can never give us that level of confidence. In the next stage, we'll learn some great features of Mocha for reducing the amount of test code we write, while also improving the quality of our test output. Writing unit tests might seem like magic sometimes, but in the end, we are still just writing JavaScript. You'll want to follow the same best practices you use when writing any JavaScript program. We should keep our tests dry and tidy. In this stage, we'll explore some handy ways to avoid repeating ourselves. We'll also expand our tests to build our confidence in the code we've written so far. So far, I've been writing the dependencies for every test within each spec. For example, in our check for ship test suite, I wrote a new player object for every test. So the first test has a player, and the second test has the same exact player. So we need this code to simulate a player object to test the check for ship function. In other words, the check for ship function doesn't work without a player object. So we need to fake or mock a player object in order to test the function. So as you can see, duplicating this code in our test file goes against the programming best practice of don't repeat yourself, or dry. Fortunately, Mocha, like all testing frameworks, comes with a few useful functions to help us set up conditions for our tests, like creating test objects and simulating the conditions inside our app. This is called the setup phase, the part of our tests where we set up conditions for testing. In fact, Mocha splits this setup process into two blocks: the stuff we set up before the entire series of tests, and the stuff we set up before each individual test. Let me show you an example. The check for ship function doesn't alter any other code. It doesn't have side effects on our player object or ships. It doesn't make changes anywhere. It just does some calculations and then gives us a report back. It says false if there's no ship at the given coordinates, or it tells us which ship it found if there is one. So because check for ship won't change a player object in any way, it's safe to set up a single player object once with the information we need, and then use that for all of the check for ship tests. So the first thing I'll do is initialize a player variable at the top of the test suite. So right after I import the check for ship function, I'll type var player. Then right below it, I'll set up a before block. So before just needs one argument, a function that runs before any of our test specs to set up any state they need. In this case, each test spec needs a player object with a ships array. So I'll simply cut the player object out of this first test spec and paste it into my before block. So now the first spec will have access to the same player it did initially. And before anything else happens in my test suite, Mocha will make a player object for all of the specs below to use. Pretty cool. So now I can go ahead and delete the player object from my second spec too, because it will use the same player object the first one used. Now, to repeat this for the other specs, we have to make sure we're keeping all the added complexity those tests need in this player object. So for instance, when I get to the third spec, I see that the player object up here in the before block is going to need a bit more complexity for our test suite to work, because I see that this ship needs a second location. And in fact, the next test spec needs a bunch of ships. So what we'll do is take the most complex player object in this suite and use it up here in our before block. So the last spec in the check for ship suite represents the most complicated object we need for any of our specs. So I'll cut the ships array used in this last spec and replace the one up top by pasting it into the before block. All right, so now all the tests in my check for ship suite will use this player object, but we only need to write it in one place, and it will work for both my complex test and for all the simpler tests too. So now I can go ahead and delete any player object in my check for ship specs. So now, since all of my test specs have access to the player object and the before block, if I run the test in the console, great, all my tests still pass. All right, so let's clean up the fire spec now. The fire function is different than check for ship. Fire is not a pure function. It has side effects in other parts of our code base. In this case, fire changes the damage array of the shipped object it's given by calling damage ship. So if we ran it over and over, we would just keep pushing damage records onto the same ship. So that means that our test specs will be altering the application state from one to another, which will mess up our expectations and maybe make them fail even when our function works. So instead of setting up a ship once in a before block, like we did earlier, we'll reset the ship for each spec. To do this, we can use a before each block. So first, I'll initialize a player variable at the top of the Fire suite. So right after I import the Fire function, I'll type var player. Before each works just like before, only it will run the function before each spec instead of just once at the start of the whole suite. So right after the player variable, I'll set up a before each block. If I copy just the player object below into the before each block, so I'll go ahead and remove var, that means that the player object will be overwritten before each test. So no matter what changes happen inside of the first spec, it will all be erased and set back up new for the next spec right here. That makes our application state predictable between specs, even when the function we're testing has side effects. A nice bonus of using before and before each blocks for setup is that our suites feel easier to read. We can see exactly how the test author thinks this function needs to work. It acts like a little bit of documentation for how the function is intended to be used. So if I save my file and run the test again in the console, nice, all my tests still pass. So in the next video, we'll cover the last phase of a test suite, teardown. Once your test suite runs, you won't need the setup variables or objects any longer. In fact, if you leave those around, they might interfere with other tests that run later. That's why Mocha provides a teardown phase to remove unwanted variables. In addition, if your tests change your development environment, like creating a pretend database or start up a local server, you can use the teardown block to set your system back to where it started. You'll need teardowns more often when your tests need a pretend database or they interact with the DOM somehow. For example, you might be testing a function that sets up a new remote database, creates a local file, or starts a server instance. When these functions are doing their job, they end up polluting your database or host service with a bunch of junk testing tables and files. In that case, you'll want to take apart any changes your tests make so that the tests further on start with a clean slate and your external systems don't get crowded with test results. Sometimes that really is what you need to do, but if you find yourself depending heavily on the teardown phase, you should double check that you're testing the right kind of function. For example, developers often rely on an external library like jQuery or React to deal with the DOM. We shouldn't be writing tests to make sure the add class function works correctly. That function has already been thoroughly tested for us.
We should also definitely try to avoid passing state between our test suites. That adds unnecessary complexity and room for error. Remember, our tests should not be clever. They don't need to do anything fancier than report our basic expectations.
Our Battleship engine doesn't rely on an external database or write files to our machine. It only needs a few objects in memory. We saw in the last video that JavaScript objects can just be overwritten in the before and before each blocks. So instead of destroying our object, I'll show you how to use the after and after each hooks to print a message in our test output. Mocha's after and after each hooks work exactly like before and before each, except that they only happen after. So in the Fire suite, right below the before each block, I'll add an after block by typing after. Now, after takes one function that will run at the very end of the test suite when every spec has finished. Inside the function, I'll add a console.log that says entire test suite completed. So now, right below the after block, I'll create an after each block by typing after each. And just like after each takes one function that runs at the very end of each test spec. So inside this function, I'll add a console.log that says 1 unit test completed. All right, so I'll save my file. And if I run my tests in the console by typing npm test, you can see the message 1 unit test completed after each individual test. And then we see entire test suite completed at the very end of the block. Perfect.
Writing tests first as an outline can help us a lot in the development process. Sometimes you'll also have to write tests for existing code. It might have been written by other people, or you might have skipped the testing phase during a chunk of your workflow. You should write tests retroactively, just the way we have been in BDD. Decide what the function does and focus on that part rather than the implementation details. Write simpler expectations first and get them to pass before you write more involved ones. One difference is that you might get to testing for an edge case faster than you would during BDD. An edge case is a radical situation your function might end up in, but it isn't how your function would normally work. For example, an email validator might work when users type properly formatted emails, but what if they type in nonsense by accident? An X-ray machine should accurately produce the amount of radiation a doctor asks for, but what happens if a doctor accidentally asks for a huge amount? So far in our test suite, we've assumed that our functions will get the right kind of input. For example, we always call check for ship using a valid player object and an array with 2 numbers. But what if something changes later, or someone tries to use our functions in a way we didn't intend? To show you what I mean, I've added a new function to our engine.
To follow along using the latest workspace, launch the workspace on this page, or you can download the files if you're working outside of workspaces. So players need a way to put their ships on the board. For each ship, they should be able to name a starting square and a direction, and save the ship's location for the game. In the latest files, I've added a test file in the test directory named playertest.js. This new file contains a test suite for each of these new functions. So here we have validate location, then validate locations, and right below place ship. Now, since you haven't seen these functions yet, it's a good idea to run the tests first and see what information they give us about the new functions. So over in the console, I'll run the new tests in the player.test.js file only by typing the command mocha test /player_test.js. So immediately we get a lot of information here. We have the 3 related functions, validate location, validate locations, and place ship. Now, validate location sounds like it confirms if a single given coordinate is not occupied yet and is on the board. And validate locations sounds like it runs validate location on a list of coordinates. And place ship takes a ship and changes its starting location. It responds with false if the proposed location would run off the board or overlap another ship. So without even looking at the code, I have a good general sense of what these functions do, how they work, and how they're related. So now let's dig into the test code. So this is a new idea. This time, I wrap the entire test suite inside a describe block that names the suite. That makes it easier to see that these tests are grouped together when I run npm tests, and all of my test results are printed to the console at once. As you saw earlier, inside the main describe block, I have tests for the validate location and validate locations functions. Feel free to pause the video and read these carefully, but we can skip over them for now. Instead, let's focus on the main function being tested, place ship. So in this suite, I import the place ship method, then set up a new player object before each test spec. And notice that the player ships have a new property of size. And there's one test spec in place here. It places the player's first ship at 0, 1 and expects the ship to have one location at 0, 1. Again, we haven't even looked at the actual code for this function at all, and we already have a good understanding of what it does and how it works. So we know that it works when everything is used as expected, but what happens if it's used in some way we didn't expect? For example, the function expects 4 arguments. Now, it's conceivable that someone might forget to use them all in the future. For instance, what happens if we don't pass a direction? Will the function throw an error and crash the game? Will it quietly add some nonsense like undefined or not a number into our ship's location? Or will it return a request for a new location? Excluding an important argument like this is an edge case. Ideally, this would never happen, just like ideally people would always enter valid email addresses into forms. But as developers, we can imagine it happening pretty easily, so it might be nice to test against this possibility. Now, we don't necessarily have to build a handler into this function, but we should definitely know what to expect when it happens. Having a test in place will demonstrate to other developers, or our future selves, what we're thinking about in this case. It might also provide useful guidance to them if they do decide to handle this case in the function later. It will be like we wrote a BDD outline for them already. So inside the place ship test suite, I'll create a new spec right below the existing spec. I'll name this spec should throw an error if no direction is specified. So now let's check the chai docs to see if there are any useful expectations I can use here. First, I'll do a search for error. Now, the first result shows up under the method not, but I see something that looks useful here. Here it says to not throw error. Now, I don't quite understand how to use the throw method yet, so I'll do a search for throw too. And cool, this tells me everything I need to use the throw method with lots of examples. So it looks like the throw method requires me to wrap my function in something that chai can handle internally. Now, if I didn't do this, then my test spec would always fail because place ship will throw an error. Mocha will think that error counts as a test failure, even though the error is really what I expect. So inside this new spec, I'll trap the error in a new function called handler that chai will manage from within and prevent the error from failing the tests. So we'll say var handler. And inside this function, we'll call place ship. And I'll also go ahead and save the ship and coordinates variables inside the spec. That way, the function call below will be a little easier to read. So now I'll pass only 3 arguments to place ship with no direction string specified. we'll pass player, ship, and coordinates. And now I can expect the handler function to throw an error. So right below, we'll say expect handler to throw error. So now if I save my player test file and go over to the console and run the same test as earlier, we can see that the test fails because the place ship function doesn't currently throw any errors. So I'll open up the playermethods.js file inside the GameLogic folder and add a line at the top of the place ship function. So we'll say, if there's no direction specified, throw an error. It's nice to give errors a useful message, so I'll pass one in here. We'll say, you left out the direction. I need that for math. So now, if anyone ever messes this up in the future, they'll get an informative error about the problem. And if I go over to the console and run the test now, we can see that everything passes. Perfect. So the chai docs for throw show me that I can also specify the error message I expect. So back inside the new spec in playertest.js, I'll write an extra expectation that specifies that. So we'll type expect handler to throw. Then I'll write the error message I expect, which is, you left out the direction. I need that for math. Predicting edge cases can be challenging. I could imagine all sorts of ways that our functions so far could fail. Web development is hard, so pretty much anything can go wrong. Now, I don't want to pollute my test suite with tons of edge cases that don't really have to do with the main functionality of my functions. So instead, you should spend a little time thinking about the edge cases that are more likely to come up. Think about problems that would be really hard for another developer to notice, or that would break your programs really badly. If you can run a test for an edge case or two like this, that's often enough at first. Pushing yourself to think about the problems that other users or developers might have when dealing with your code will also make you a better developer and result in better software. So it's good for you too. One of the best things about BDD is that our code is always testable. It has to be because we always write our tests first. But if you end up with code before tests, it can be hard to make a meaningful unit test for existing functions. That's because some code is not testable. The particular nature of JavaScript means that we have access to some code and not other. To demonstrate this, in the latest project files for this challenge, I've written a pair of functions that handle a computer player. To make a computer player, we have to give it a programmatic way of placing ships without us knowing, and guessing locations during their turn. So I've named these functions computer place ship and computer fire. I want to write tests for these to make sure they work, but the problem is that they produce random results. And that's the whole point. If the results weren't random, then playing against the computer would be predictable and no fun. So if I write a new suite for computer fire in playertest.js, what would I expect to result from the function? If the random location it chooses has a ship, then I should expect that ship to be damaged. But if the random location does not have a ship, then I should expect the ship to not be damaged. I can expect that one of those will happen, but that's not very meaningful. It wouldn't tell me much about what the function is doing to say expect ship.damage to have length of 1 or expect ship.damage to be empty. So the way computer fire is written is not testable. The only tests we can write for it are trivial and uninformative. But we know a lot about testing now. So by looking at the two computer functions I've written, maybe you can find a way to refactor them so that they're more testable. try to rewrite the set of functions so that we can still generate random functions. Now, you might need to move the code generating random numbers into their own functions in order to isolate the problem. And in the next video, I'll show you my idea for getting the code to be more testable. So the problem with computer fire and computer place ship is that they have random outcomes built in. Each of these functions really does two different things. First, they build a random location, then they do something with that location, like fire a shot or place a ship. In programming, we call this tight coupling, when two distinct functions are bundled up so that they can only really be used together. Now, a hallmark of tightly coupled code is that it makes our job of writing unit tests harder. So to refactor this code, I think we can actually just abstract those two ideas apart. We see that the same code appears in both the computer fire and computer place ship functions, the part that generates two numbers in the board range and puts them in an array. So we can pull that out into its own function that returns the result. Let's call the function getRandomCoordinates. Then I'll cut the variable declarations for x, y, and coordinates out of the computer fire function and paste them inside getRandomCoordinates. So now to put the x and y numbers in an array, instead of var coordinates equals xy, we'll say return xy. So now I can delete these from computer place ship as well. So computer place ship also randomly chooses horizontal or vertical. So we can use the same strategy by pulling out that logic into a separate function. Let's call this function getRandomDirection. So now I'll go ahead and cut the direction declaration out of computer place ship and paste it inside getRandomDirection. And in this function, instead of var direction equals math.random, we'll say return math.random. So at this point, there's actually nothing left of our original functions besides a call to fire and place ship. So at the bottom of our file, we can remove the module.exports for computer place ship and computer fire. But now we can also use the randomizers with the existing fire and place ship functions in place of the original computer functions. So, for example, we can set up the game to call fire and place ship with some attempted random coordinates in between human player turns, like this. We also get to use these randomizer functions in other parts of our game engine if we need to. That's a big plus. More reusable code will save us time later. And this way, we don't have to add any tests at all. In fact, this is another thing that writing tests helps us with. When it's hard to write tests for something, you might wonder whether you really need that function in the first place. In this way, writing tests can guide us towards simpler code. We still can't do a super meaningful test for the randomizer functions because of their random nature, but we've pulled the random pieces apart from our other application code so that our other parts remain testable. Thinking about good unit tests has improved our code yet again, making it more reusable and modular. We've learned a lot in this stage: setup and teardown in our test suites, testing for edge cases, and keeping our code decoupled and testable. So you're ready to use Mocha and Chai to keep doing BDD in your applications. In the last stage, I'll show you some other convenient ways to display your test results and introduce some more advanced features of Mocha. We've covered a lot so far.
using BDD to lay the groundwork of our battleship game, using Mocha and Chai to write unit tests for code that already exists, setting up test suites and test specs with Mocha's describe and it blocks, and writing test expectations with Chai's expect method. But there's a lot more that Mocha can do. In this stage, we'll wrap up by looking at some of Mocha's extra tools. Let's get started.
So far, we've been looking at Mocha's default reports in our console. They're much easier to read than standard JavaScript console.log statements, but there are other options too. For instance, you can change the reporter style using the reporter flag when running Mocha. A good use of the reporter flag is when you only want to see test failures. When you have lots of tests running all the time, you might not care to see all the specific passing tests in your console. So to show only the failing test errors, you can use mocha reporter min. So in our console, now Mocha only prints 15 passing. But if I change one of our expectations to fail a unit test, then Mocha will print the same error report we're used to seeing and hides the passing tests. So for example, in main.test.js, I'll change expect true to be okay to expect true to be false so that it fails. So when I save the file and run the same test again, Mocha now prints 14 passing and 1 failing, followed by the usual error report. So another cool reporter is the Markdown reporter. Mocha reporter Markdown will print the same long test report we're used to, but using Markdown format. That means you can just copy and paste it into the README file for your GitHub repo and use the passing tests as pre-written documentation. This may help other developers understand how your code works without them having to download and run the tests. Go ahead and check the teacher's notes to learn more about the Markdown format if you'd like to learn more. You can browse all the possible reporting mechanisms in the Mocha documentation. Now, some of them are just for fun, and others, like Markdown and Min, are useful in different situations. So try some out and share your favorites in the community. I personally like the 9 reporter. I think it's pretty awesome. And if you find one you like better than the defaults, you can add a reporter flag to your package.json file in your test command, like this. This way, npm test will always use that reporter. Neat.
In some ways, being a programmer is more like being a writer than being an engineer. It requires a lot of creativity, and you can get stuck a lot waiting for inspiration to strike. A nice feature of Mocha is that we can outline tests that need to be written still before we're ready to write them. So when you have an idea for a test, but you don't have time to figure it out, or you aren't yet sure what it will look like, you can still communicate your idea to other people and get started. Let me show you an example.
In order to play a game, it would be nice to have a function that checks whether the game is over after each turn. That way, every time I make a guess, the game engine will check and see whether I've struck the last ship and won, or whether the next player should start their turn. I know I need that, but I'm not ready to think about how it works yet, not even to write the tests. So I can write a pending test spec to keep track of those tests I have to write later. Inside the test folder, I'll create a new test suite file called gametest.js, since this suite will focus on functions pertaining to the flow of the game. So first, I'll import chai at the top of the new file so that we can use it here as an expectation. And now I'll set up the fundamental describe block for this suite. And as the first argument, I'll write game instance functions in all caps. This is only here to make the output nicer for me. I'll call the function I'm testing here check game status, so I'll create a new test suite for it. Now, a test spec that I know I should write for this function confirms that it should tell me when the game is over. So I'll create a new spec that says it should tell me when the game is over. This is a pending test. So in order to mark this test as pending, I do not add a function as the second argument. The it block is only written with the first argument describing the test, and it doesn't contain any expectations yet. So now if I go over to the console and run npm test, it shows me that I now have 15 tests passing and 1 pending. Notice the pending tests are in a different color, so they're easier to see. In my console, the test is light blue. This is really useful as a reminder to myself and others that some tests need to be written still. It's like having an outline for my outline. It communicates some information for getting started. I can also mark tests as pending by typing an X in front of the pending block, like xDescribe or xIt. For example, if I add a regular test spec to my current suite, even though I've added a function as a second argument, I can add X in front of the describe block, and all of the specs inside will be marked as pending. I prefer leaving out a callback to using xDescribe because I don't have to delete anything later. I just have to continue writing the test spec as I normally would. You might see this done both ways, so feel free to use whichever method you like better. If you're like me, you might be annoyed that you have to type npm test every time you want to check whether your changes pass or fail the tests. So Mocha comes with a special watch flag that will automatically run any specified tests when it sees changes in a certain file or directory. For example, when you launch the latest workspace or open the project files for this video, you'll see that I filled in the spec we started writing in the previous video for the check game status function, but I still haven't finished the function itself. So when I run check game status on a player with 1 sunken ship, then the game should be over, and check game status should report false. So while I'm building this function, I want Mocha to automatically run my tests every time I make a change to check game status, so that I'll know right away when all my tests are passing. We can do just that with the watch flag. I've set up the initial function in this new gameinstance.js file located inside the GameLogic folder, and running npm test in the console shows that the test fails. So it really breaks up our workflow when we have to write code, switch to the console, run npm test, see the output, and switch back. We might make a lot of changes to our function, and it would be nice to know right away when something works or something breaks. So to watch my gameinstance.js file, I run Mocha with the watch flag. I need to tell Mocha which test to run and which file to watch. So in this example, if I run Mocha -- watch, followed by the path to the game test file, then the path to the function file, Mocha will run the suite found in gametest.js every time I save a change to the file. It runs right away, and I see the original failure. So inside gameinstance.js, if I set the check game status function to return false and save the file, we see the console automatically runs the test again, and now they're passing. Pretty cool. So you can write custom Mocha watch commands like this
whenever you plan to be working on one particular file a lot. But you can also save a general watch command in your package.json file to run your tests all the time while you work. That might be helpful for you to check whenever you're unsure what's working and what isn't working in the big picture while you build your application. So to set that up, let's go ahead and open up the package.json file. So in your script section, after test, let's add a new command. So first, we'll type test:watch. The command we want here should run all of our unit tests whenever we make changes anywhere. So let's try Mocha --watch, followed by space, then period/test, followed by space, then period/. Remember, the first argument describes the tests we want to run, all the tests in the test directory. And the second argument describes the files we want to watch for changes, so all the files in the current directory. And don't forget to add a period at the start of your file path, or Mocha will get confused on which files you're looking for. All right, so I'll go ahead and save my package.json file, then bring up the console. And now when I run npm run test:watch, Mocha starts running all my tests and watches for any file changes in my project. So great, I see all my tests passed at first. So now, if for example, I open up the main test.js file and change an expectation to fail, so let's say expect true to be false. When I save the file, we immediately see the failing test results in the console. And if I change it back to OK, save the file, I see the passing test results again. And if I open a game logic file, like playermethods.js, and comment out some important code, once I save the file, I see the tests are failing again. So if I uncomment the code and save, all my tests pass again. Cool. So this is really useful. And now to stop running watch, you can go over to the console and type Control-C. So if you have a lot of tests, you might want to adapt this command so that it doesn't run them all every time you make any change. You can change a command to be more specific to the part of the code you're currently working with to save time and improve performance. And in your package.json file, you can even set several different commands like test:watch player methods and set it to watch only playertest.js and playermethods.js. That way, it's easy to watch different things at different times. You've seen a lot of testing material. Let's wrap up with some talk about advanced testing features you might use in the future. A big part of writing effective tests is making sure that your tests focus on one clear behavior. If your tests have a lot of external dependencies, then it's hard to know whether they're failing because of the function you're meaning to test, or if actually one of the dependencies is failing. That makes the test less powerful in debugging because you might have to check functions other than the ones named in your test spec. You may not be sure where to start. For our outlining, we've also seen that it's sometimes helpful to pretend that we know how certain functions work in order to get started. We can take this idea even further with mocks and stubs. Mocks and stubs are two special kind of fake helpers for our test suites. We've been using fake helpers all along with the fake objects we set up before each test. Mocks and stubs are fake functions that fill in the gaps for our test unit's dependencies. Now, developers don't always agree about the difference between mocks and stubs, but I've posted some links in the teacher's notes that you can read to get a sense of the distinction. In this video, I'll show you a stubbed function to get you started thinking about more complex testing. We still need a function that will let players take their turn. That function should ask the current player to guess a location, fire on that location, and then check whether the game is over afterwards. If it is, then it should return something to stop the game, because the game is over. And if it isn't, then it should return something that lets the next player take their turn.
Notice again how I don't really know yet all the details of this function. I'm just making educated guesses about it to describe its general behavior. So in gametest.js, inside the game instance function suite, I'll create a new test suite for that function. I'll call it takeTurn. So here at the top of the suite, let's import the takeTurn function that will eventually be written in the game instance file. For my first spec, I'll test that takeTurn returns false when the game ends. So we'll say it should return false if the game ends. This function combines several behaviors: guessing, firing, and checking the game's status. We've already tested fire, but we haven't yet implemented any functions that take input from the player. That's because we don't know yet about how it will be played. Will it be in a browser? Will it require manually typed commands? Will it use a game controller? So we've kept our game engine in the dark about these questions so that we can use it in a variety of environments. So using stubs will let us test logic that depends on these decisions without having to actually make them yet. For example, the takeTurn function will probably call a guess function to decide what happens next. Since I haven't written these yet, I can introduce a variable called guess at the top of my function, just like I've been doing for player and ship objects. So next, I'll create a before each block right above the spec here. In this block, I can set guess to be a pretend function that doesn't do real game logic. Now, I call these pretend functions because they just return the values I would expect the real working functions to produce. Guess will gather a location from the current player that they want to fire a shot on. This could be from a click in the browser, or typed in the command line, or some other method. Maybe it will even be spoken into a microphone, who knows? So no matter how players interact with guess, it will somehow need to return a valid coordinate. So that means I need to set guess to be a function that returns a valid coordinate. So inside the before each block, we'll say guess equals function. And inside the function, we'll return the coordinate 0, 0. So now, no matter how I write guess in the future, this test ensures that takeTurn does what I expect with the return value. Finally, takeTurn needs to know which player is taking their turn. So I'll initialize a player variable at the top, then pass in a player object in my before each block. I'll set a ships array as a property on the object. Then I'll add a locations and an empty damage array to ships. So now, inside the spec, if I call takeTurn with a player and the player guesses the last ship location of their opponent, the game is over. So I'll call takeTurn and pass player and guess as arguments and save it to a variable named actual. And again, if the player guesses the last ship location of their opponent, the game is over. So in this case, takeTurn should return false. So we'll say expect actual to be false. So now, even though I have no working guess function, I've set up this spec to pretend that those parts of my code already work. That's the only important information this test needs. If I bring up my console and run my tests, my test fails. It says takeTurn is not a function. So now I'll jump over to gameinstance.js and write the take turn function here. So right below check game status, we'll say function take turn. The take turn function will take a guess function callback, and it will use this to save a guess. So we'll save guess function in a variable named coordinates. The function will also take an opposing player callback to fire on the opposing player at those coordinates. So we'll also pass opposing player. Then in the function, we'll call fire, and we'll pass opposing player and coordinates as arguments. So now, up top, we'll need to import the fire function from shipmethods.js. So next, to check whether the game is over, we'll declare a game over variable, which calls check game status. And in the end, the function returns the resulting status of game over so that we know whether to let the opposing player take their turn. So we'll say return game over. And finally, we'll export the take turn function here at the bottom of the file by typing module.exports.taketurn equals take turn. All right, so let's save our file, bring up the console, and run our tests. So great. Even though guess has not been written, my test passes. The test spec used my stub version of the guess function instead, so it got all the values it needed just for testing my logic. So now I know that the logical structure of take turn is correct, so I can move on to writing something else.
Another benefit of this stubbing is that even while I'm working on the check game status and guess functions, tinkering with them to do this or that, my take turn test will keep passing. Take turn gets the value I ultimately expect those functions to return, no matter how those functions actually work. There are whole libraries dedicated to making stubs easy to write, like signin.js. Signin lets you set up pretend servers, HTTP requests, databases, and more. So if you want to learn more about mocks and stubs, you can check out Signin's homepage to see many more examples. Testing asynchronous functions can be a unique challenge. Our Battleship game doesn't have any asynchronous elements, but we might want it to. For example, if it were played across an internet connection on two computers, one player would have to wait for the other's turn. If we wanted to save our game somewhere and start again later, we'd need to connect to a database that stored our game state. Those processes would probably be synchronous for efficiency.
Mocha allows us to say that a test spec or test suite is asynchronous. So passing an argument to the internal function of a describe or it block will tell Mocha to wait on running our expectations until we specifically say so. Let me show you how it works. I'll create the function inside the main game instance function suite, right below the take turn suite. Now, in this function, we'd normally have to write some code to communicate with a remote database, but instead, I'll simulate that idea with a set timeout function. So set timeout will perform whatever function we describe after a specified number of milliseconds. If our game really communicated with a database, the set timeout function would be replaced with something that sent a request to our database. So I'll set the function to run after 1 second has passed, or 1000 milliseconds. So after 1 second, the database function would finish and perform some callback, like telling the player that the game was saved successfully. So let's pass callback as a parameter of save game. Then we'll call callback inside set timeout. All right, so now we can create the test suite for save game. So right below the save game function, As always, we'll create a new test suite by typing describe, and we're going to name this one save game. And then I'll open my first spec for this function inside the suite. So we'll say it should update save status. And now I have a space to write some expectations about how save game should work. So to test synchronous functions like the ones we've written before now in the course, I would run the function inside of my spec and then write an expectation about something that changed as a result. So to use that strategy in this case, I might try running save game with a callback and writing an expectation at the end of the callback to capture the new results. So let's do that. At the top of the spec, I'll save the string game not saved in a new variable named status. Then I want save game to change the status to game saved when it finishes. Again, in reality, that would mean the database responded successfully. But in this example, it's just going to wait 1 second and then use my callback function to update the status variable. So inside save game, we'll say status equals game saved. Finally, I'll try expecting the status to equal game saved after I've called save game. So right below save game, we'll say expect status to equal game saved. So now if I bring up the console and run my tests, we can see that the test reveals a failure. The expectation runs before the save game function is called because save game is waiting 1000 milliseconds to fire the callback that updates status. So that means status will still equal game not saved until an entire second has passed, which we can see it's much longer than our test suite takes to reach the expect status line. So to fix this problem, I need to move my expectation inside the save game callback so that it only happens after save game has finished updating status. So now if I go back to the console and run my test at this point, it looks like the tests pass. But that's kind of tricky. Mocha is just running through the test function before save game finishes, and then it reports that the test spec passes because it didn't see any expectations written. So for example, even if I write a definitely failing expectation into the save game callback, like expect true to be false, Mocha still passes our tests. So we need a way to tell Mocha to wait until save game has finished running in order to check our expectations. To do that, I can pass a special argument to our test specs callback function. By convention, we call the argument done so that we know the argument is signaling Mocha that our test code is ready to be run after some asynchronous operation. We normally just use the test spec callback to contain our test code and expectations, but by passing it an argument, we signal to Mocha that we want this test to run asynchronously. So now I'll delete this example expectation, then run npm tests. And now we see that the test gives me a new error. It says save game should update save status. Then the error says timeout of 2000 milliseconds exceeded. Ensure the done callback is being called in this test. So it looks like the error is asking for me to call the done callback. Passing the done argument to our test spec tells Mocha that it's supposed to wait for our instructions before checking our expectations. So we passed the done argument, but we haven't used it to tell Mocha when our code is ready to be tested. So in the save game callback, I'll add done after the changes I expect to occur. And now Mocha will wait for done to fire before checking the expectations. So when we run the tests now, great, everything works. And notice that there's a short pause while the tests are running. That's Mocha waiting 1 second for the set timeout function to run before checking the expectations.
Writing asynchronous code and testing it correctly is a big topic. Usually, you'll write mocks and stubs for your database or AJAX calls because those are big external systems that you don't want to mix into your test unit. Just know that Mocha gives you a way to deal with these problems, so you might need to research the best way to capture the test results you want when you encounter them. So congratulations getting started with JavaScript unit testing. Good unit testing takes practice, and there's a lot more you can learn and do to improve the quality of your test, and also to make writing tests easier. If you've never written any tests, this testing first approach is different from what you're used to, and at first it can feel like a lot more work. As you get better, writing unit tests really will improve your code. It will also save you lots of time fixing bugs and explaining things to other developers. So dig into Mocha and Chai and let us know in the community when you find useful tips and tricks. Good luck and happy testing.